AI Interview Prep, Episode 34, AI Multimodal Systems, How Senior Engineers Build, Deploy, and Scale Vision Language Models in Production. Welcome back to AI Interview Prep. I'm your host, and today we're covering one of the hottest topics in 2026 AI engineering interviews, multimodal systems. If you're interviewing at companies building with GPT-4o, Gemini, or Claude, or building your own vision language pipelines, this episode is essential. Let's get into it. Section 1. What interviewers actually want to hear. When an interviewer asks you about multimodal AI, they're not testing whether you know that multimodal means multiple input types. They want to see that you understand the engineering complexity, latency, throughput, pre-processing pipelines, and failure modes. The answer that gets you hired sounds like this. I'd separate the modality encoders, vision, text, audio, as independent services, normalize their outputs into a shared embedding space, and route the fused representation through the LLM backbone. That gives you independent scaling, isolated failure domains, and the ability to swap encoders without redeploying the whole system. That's engineer mode thinking, not just we feed images and text together. Section 2. The core architecture pattern. Here's the standard multimodal architecture that appears in most production systems. First, the encoder layer. Each modality has its own encoder. Images go through a vision transformer, like SigLIP or SigLIP. Text goes through a standard tokenizer and embedding layer. Audio, if present, goes through a whisper-style encoder. These run in parallel, independently. Second, the projection layer. Raw encoder outputs live in different dimensional spaces. A lightweight MLP, typically two linear layers with a nonlinearity, projects each modality into the LLM's embedding space. This is where the magic of alignment happens. The model learns that an image of a dog and the word dog should be close in representation space. Third, the fusion strategy. There are two dominant approaches. Early fusion. Concatenate all modality tokens before the LLM processes them. Simple, flexible, but expensive. The LLM attends over everything. Late fusion. Each modality gets its own LLM pass, then you merge at the final layer. More compute, but better for independent reasoning. For most production systems, early fusion wins on latency. Late fusion is better when you need independent confidence scores per modality. Fourth, the LLM backbone. This is unchanged. Your GPT-4 class model receives a sequence of tokens, some from text, some from vision projection, and generates a response. The model doesn't know or care which tokens came from which source. Section 3. The interview question you will get. Design an AI system that can answer questions about uploaded documents, PDFs, images, screenshots, in real time. Here's how to structure your answer. Start with the ingestion pipeline. PDFs need text extraction. Use Plumber or PyMup for native text, and a vision model for scan documents. Images go through OCR as a fallback. Audio transcription via Whisper if needed. Then chunk and embed. Split extracted content into semantic chunks, about 500 tokens each, with 50 token overlap. Embed using a multimodal embedding model. Store in a vector database, Pinecone, Weaviate, or PGVector depending on scale. At query time, embed the user's question using the same model. Retrieve top K chunks. Build a context window with retrieved chunks plus the original query. Stream the LLM response. The key insight to drop. I'd use a multimodal embedding model, one that was trained on image-text pairs, so image content and text content land in the same vector space. That means I can retrieve relevant image chunks using a text query, without needing to OCR everything up front. That answer signals you've shipped this before, not just read about it. Section 4. Scaling challenges and how to answer them. How do you handle latency for vision inputs? This is where junior and senior engineers diverge. The junior answer. We use a fast vision model. The senior answer has three parts. 1. Pre-processing caching. Images are expensive to encode. Cache the vision encoder output keyed by image hash. If the same screenshot appears twice, you skip the encoder entirely. 2. Resolution tiering. Run a fast low-resolution pass first. If confidence is low, escalate to high resolution. This cuts median latency dramatically while maintaining quality for hard cases. 3. Async prefetching. In chat interfaces, users often upload images before typing their question. Start encoding the image the moment it's uploaded, not when they hit send. By query time, the encoder output is already cached. Combined, these three techniques can cut P99 latency by 60 to 70% in real-world systems. Section 5. Failure modes interviewers love to probe. What goes wrong in multimodal systems? First, modality imbalance. If your training data has 90% text-image pairs and 10% audio, the model will underperform on audio queries. In production, you need to monitor per modality accuracy, not just aggregate accuracy. Second, context length overflow. A single high-resolution image can tokenize to 1,000 plus tokens. In a long conversation with multiple images, you'll blow past the context window fast. You need an image eviction policy. Keep the most recently referenced images, summarize older ones. Third, hallucination on images. LLMs sometimes see text in images that isn't there, especially with low contrast or unusual fonts. Add a confidence threshold. If OCR confidence is below 85%, flag the output for human review rather than presenting it as fact. Fourth, cross-modal inconsistency. A user sends an image of a chart and asks a question. The chart says 42%, but the LLM answers 44%. This happens when the vision encoder and the LLM disagree on pixel-level details. Mitigate with structured extraction. Parse the image into structured data first, then answer from the structured data, not the raw image token.